back. So he went away to Caltech to do his PhD with John Hopfield, and then he was in London with Jeff Hinton, who was his postdoc advisor, and now his colleague back in Toronto again. And in between, you seem to have done stints at Whizbang and Bell Labs. So he's sort of been at most of the worthwhile places, and now he's here. And he's worked on sort of the spectrum of things that you might expect somebody who really likes models and algorithms to do. So if you want to do parameter estimation or inference over interesting models that are well suited for data user.
Well, thank you, Jason. It's great to be here. I was here many years ago for Workshop 96, and I have since sort of forked my life into a speech part and a machine learning part. So today I'm going to tell you about speech, although as I talk to people, I realize that maybe working on speech is not the cool thing to do anymore. I should be working on machine translation, but I'll have to get going on that. Anyway, I wanted to tell you today about a general sort of approach to doing speech processing tasks, mostly low-level speech processing tasks, which makes use of the technique of inference in a generative model. So this is probably familiar to most of you, but just to get us started. So generative models are probabilistic or stochastic state machines which produce outputs that look like the ones that we observe. That's why it's called a generative model. So for example, you can think of a hidden Markov model as a generative model for a vector time series. So it's a machine that you run, and it spits out a vector time series. And given the parameters of the machine and some observations, we can perform an operation called inference, which is to ask ourselves, what do we think the best state sequence in the machine it would have had to have been to generate the data we saw? Okay? So that's asking, of all the ways that the machine could have produced the data, what's the most likely? That's one question. Or summed over all possible internal trajectories the machine could have taken, what's the chance that we would have gotten the data? That's another related inference question. And these are answered in the case of HMMs by the forward, backward, and Viterbi algorithms. So you can imagine that there are some parameters here. There's the internal states of the machine, and then there are these observations. And the thing I want to try and brainwash you into believing today is that inference is actually a signal processing algorithm. But it's one that's automatically derived for you by the rules of probability and statistics. So don't think of inference as answering a question about the internal states of some model. Think of inference as a sequence of operations that you do when you get X to give some answer, which happens parenthetically to be your estimate of S. But that's just a parenthetical thing. Imagine that it's an automatic signal processing algorithm. And the plan, which is sort of ludicrously simple, right? This is a lesson to all the graduate students that even as a faculty member, you can have a ludicrously simple research idea, and you can still make some progress on it. The plan is make up a very simple generative model for your data, try and incorporate some domain knowledge along the way in which the quantities of interest appear as hidden variables or states, and then use inference to do automatic signal processing. So some of you probably think that this is a lot of hot air from some probability and statistics field, but I'm going to try and show you that this actually can be made to work. So I added this slide this afternoon because I had a very interesting meeting before lunch in which I was describing something, and I spoke about a spectrogram, and someone said, a spectrogram? What do you really mean by a spectrogram? So just for the non-speech people, imagine the multi-bit. Yes, yes. So the idea of the spectrogram is very simple. It's just a multi-band frequency analysis. So you take your signal, you do short time spectral analysis, and you lay the signal, the answer to that, you take the magnitude, you lay it on its side, and you run them. So very informally, you can think of this as a musical score. These are the keys of the piano here. This is time, and the color tells you how hard you should hit the note. Now, of course, there's some phase information which is not displayed here. But and the key point about the spectrogram in the case of speech is that information is sparsely distributed, but at the same time redundant. So if you ask for any given frequency or any given time, how many cells have substantial energy over the noise floor, the answer is not very many. But if you go and you obscure much of this energy by noise or by masking, you can still understand the speech. So speech is redundant, but also in some way it's sparse. And of course, there's a lot of structure, like there's harmonic stacking and frequency co-modulation and all these things that you know about. So I want to start off with a little bit of a puzzle. This is something you can try in the privacy of your own office in 30 seconds in MATLAB or maybe 50 seconds in ESPS waves. Take two clean speech signals and make their spectrograms. And now mix them additively in the time domain. So you just take signal A plus signal B, divide by 2. Okay? What's the spectrogram of the mixture? So that's the question. And if you try this, you'll find out that the spectrogram of the mixture is almost exactly the element-wise maximum of these two. Okay? So where this is the log of the absolute value of the short-time Fourier transform. This observation was made 20 years ago by Roger Moore in a technical report that he wrote. And the reason that this is true is exactly the reason that I was telling you earlier, which is that the speech code is redundant and sparse. So the chance that two speakers who are independent will be dumping energy into the same time frequency cell at the same time is very small. And therefore, to a good approximation, the spectrogram of the mixture is actually the element-wise maximum. You can formalize that intuition a little bit more by asking, what is the relationship between the log of the max and the max of the log? So here what I've plotted is the log of one quantity, the log of the other quantity, and I've color-coded the max. And here I have exactly the same axes, and what I've coded is the log of the sum. Okay? And you can see that these two things agree with each other extremely well. In fact, the only place that they disagree is on the axis up here. In other words, they're only in disagreement when both signals are contributing a substantial amount of energy. Now, when are both signals contributing a substantial amount of energy to the same frequency band? In order to answer that question, you could take two speech signals, and you could look across one of those frequency bands and make a scatter plot like the plot I've made here. So this is in one frequency band. Make a dot at the location in this plane with the energy of source 1 being the horizontal axis and the energy of source 2 being the vertical axis. So we just look at how much energy is speaker 1 putting into that frequency, how much energy is speaker 2 putting in at every point in time. And you can see that, where is this approximation really terrible? This approximation is really terrible out here. And there's no data out there, right? Most of the time, to a good approximation, one source is quiet and the other source is active. Actually, most of the time, both sources are quiet. That's where most of the mass in this picture is. But it's very rare that both sources are active, and that's why this approximation works. Okay? So the summary is that two unsynchronized speech signals almost never both put high energy into the same band at the same time. Okay? So we're going to take this idea and we're going to try and leverage it into a very simple signal processing algorithm to do source separation, to actually separate two speakers. So how would you ever do something like speech separation or speech denoising? And again, we can appeal to the musical analogy. Imagine that there's a piano, and I sit down on the piano and I play a song. This actually requires a lot of imagination because I don't play the piano. But, okay? And then someone else comes and they start playing on the same piano at the same time. And you're listening to this music, right? The question is, can you distinguish the two songs? Can you listen in on one song? And you all have the intuition that you can. And the reason is because there's a lot of structure in music. If we were each playing random notes, there would be no way for you to tell the difference. There'd be no way, because it was just random selection of notes. But of course, there's structure in music, so you could follow it. The same thing applies to speech. So the only way that you can do separation from a monaural recording is to use the inherent redundancy in the speech code. So essentially what we're doing is we're filling in missing time frequency energy, which is either obscured by noise or other sources. And in order to do this, what you need to do is identify which signals are reliable and which signals need to be masked out. So here's the sort of assumption that we're going to make. I want to try and isolate one auditory object at a time from the source. So imagine I give you a mixture. It might have more than one speaker in it. But really, you're just going to try and pull out one auditory object, one speaker, and put everything else in the background. And we're going to think of this, I think of this as sort of listen by numbers. So many of you are probably too young to have ever seen this toy, but there used to be a little book called Paint by Numbers. And it was like you would just fill in a whole solid color. It was like a drawing with no colors on it, and each region you would fill in with a solid color. So this is listen by numbers. Every time frequency pixel in the spectrogram is going to be assigned completely either to the source that we're pulling out or to the background. There's no partial assignments here. So you can think of the task that I'm setting you now as I give you a spectrogram, and you go and you tell me which time frequency cells in the spectrogram belong to the same object. And everything else we're going to put in the background. Okay? That's the idea. So how can you identify a collection of time frequency cells that all belong to the same thing? So this general approach to source separation is called refiltering, or masking sometimes. And the way it works is very simple. The way it works is you take your original signal and you break it into multiple bands. And on each of these bands, you apply a little gain signal. And in the simple example I gave you, we're going to make these gain signals just piecewise constant. Either we're going to gate that part of the signal out completely, or we're going to gate it in. So they're just 0 or 1, these gain signals. So you can imagine that this is the original spectrogram. You took your original signal, you did some kind of multi-band analysis, and now there's a monkey who has control over these gain knobs, and the monkey is turning the knobs, and the job of the monkey is to turn the knobs in exactly the right way at exactly the right time, so that what arrives at the output is your estimated source. So hopefully, if the monkey is doing their job properly, they'll turn down the gain when that band is noisy, and they'll turn up the gain when that band contains signal. So these signals here are the gain signals, and these are the multiple bands. And the crazy thing about refiltering is even if you make this assumption that these gains are piecewise constant, it works extremely well if you picked correctly which time frequency pixels to gate in. Now, I have to tell you that there's a little trick hiding behind here. So there's always a little trick, and it's always good to learn about these tricks because then you can use them. The reason refiltering works so well is because in addition to the spectrogram, you also have in your back pocket the phase of the original signal. And when you go to reconstruct this source signal, you're actually using the phase information. So if you just took the spectrogram and you discarded the phase, and we just did this gain on the spectrogram, and then I said, please recover for me the original source, you'd be completely pooched. But you have the original phase because you had the original signal. So that's why I've written these equations in the time domain to remind you that you should keep the phase around. Or you could do this in the time domain, or you could do it in the frequency domain and combine it with the original phase. Either way, you definitely want to have the phase there. So here is the simple generative model that I promised you at the beginning of the talk. Bill?
You have the phase of the combined signal?
Yes, you have the phase of the combined signal, but that, and this is something that, again, is subject to a little bit of debate, but in a small region, the phase is dominated by the controlling source. So if you're gating that source in, it'll have the correct phase, and if you're gating it out, you don't care about the phase anyway. That's a good question. OK, so here is the simple generative model that I promised you at the beginning of the talk. It's called MaxVQ, which stands for max vector quantization. So we're going to imagine a ludicrously simple model of spectrograms of audio mixtures. Here's the model. Each source has a vector quantizer, just a set of puzzle pieces, codebook vectors. And it generates its spectrogram by laying down columns independently. So let's say we build a VQ on my voice. The model for my voice is I just have some spectrogram columns that I lay down to generate my signal. And then we build a model of Bill's voice. Bill just lays down his spectrogram columns. And then we take the max, and that's the output. Okay? So you can think of this as a very simple model where we have k vector quantizers, if we had k sources. Each vector quantizer generates a proposal by selecting one of its codebook vectors. So we might pick this one here, and so on. And then we take the max along each dimension, and we add some noise. And let's keep the noise non-negative, so that if everything here was positive, we take the max and we add non-negative noise, we're still going to get positive things. So we can think of this all as energy. Okay? So is everyone clear on the generative model? We have these codebook vectors for each source. Each source independently picks a code word from their VQ, and we take the max, element-wise max, along each dimension. And that's how we're going to pretend that we generated the spectrogram. Now, of course, that's a ludicrous model of spectrogram generation, but the max operation is not ludicrous, as I showed you. That's real, and that's what's going to save us. Jason?
So in this model, successive frames are not correlated at all, is it?
Correct. So.
Unigrams.
Yes, it's the unigram model, if you insist on on that analogy. Zach?
Where do you get the VQ for each source?
Right. So Zach is one step ahead of me. I cheat, and I train on isolated data. But I would love nothing more than to have a way of training this model completely unsupervised. But yeah, I've already sacrificed several months of research and one master's student to that adventure, and it hasn't really panned out. But yeah, so as you'll see in a second, I'm going to say, imagine we had a bunch of training data for me. We built an HMM code book. We had a bunch of training data for Bill, isolated data, and then we got a mixture and we wanted to separate it. So how do we actually use this model? So the way we're going to do the training is to use this single source data, isolated data for each source, and we're just going to fit a regular vector quantizer to the columns. Actually, I fit it to pairs of adjacent columns, just because that gives a little bit of temporal smoothness. But this is very similar to the kind of thing you would have done in 1982 if you were doing speaker identification. It's like really simple-minded. So you just fit a vector quantizer to the log narrowband spectrogram. It's nothing fancy. And then given an observed signal, you take that spectrogram of the observed signal, and you perform inference in this max VQ model. So you go back to this model, and you say, let me pretend that every column or pair of columns in the observed spectrogram was actually generated by one of these proposals, another proposal, and then the element-wise maximum. Okay. And we use the results of inference to perform refiltering. So what do? In every column, we ask who won the race. So we ask, in the inference procedure, every vector quantizer supposedly picked one of their codebook vectors. That's what inference is going to tell us. And then we just look and we say, if inference was right, and Bill picked number 36 and I picked number 17, which one of us would have been the maximum in this frequency bin? If Bill was the maximum, we'll gate him in. If I was the maximum, we'll gate me in. So that's what we do. We ask inference for the map, for the Viterbi decoding in this model, and we just look in each frequency bin which source won the race. We gate that source in, and we gate all the other sources out. So again, these masking signals are piecewise constant, either 0 or 1. So you can think of this as a highly non-stationary Wiener filter, right? It's just re-estimated every 30 milliseconds, and the assumption is locally that the signal and the noise spectra don't overlap. That's a kind of, if you're an engineer, this is a kind of crazy way to think about it, but that's really equivalent to what's happening. So I just want to show you some very simple results. And I'm not implying, I really want to emphasize this now and also in the later part of the talk, I'm not implying that these are state-of-the-art results for denoising or for separation. There are better algorithms for doing all of these problems. What I'm trying to convince you of is that a super simple generative model combined with inference can get you surprisingly good results. Not state-of-the-art, but surprisingly good considering how stupid the original model was. So here's a noisy segment of speech, and we just mixed some Timmett speech with some data from the NoiseX database. This is what spectral subtraction would do if you knew the true spectrum of the noise. This is the original noiseless signal, and this is the recovery that our denoising algorithm gives us. You train a VQ on the noise, you train a VQ on the speaker, and this is a test utterance, obviously, a new utterance that's never seen before. This is the denoising. And if you open up your MATLAB hood and you peer inside and look at what's happening, you ask, what did inference think? Inference thought that in order to make this signal, the noise vector quantizer picked these code word vectors, and the speech vector quantizer picked these code word vectors. Now, here is the point which I cannot emphasize strongly enough. This and this are terrible models of the data. They look nothing like the spectrum, right? They're all blurred and low resolution. This is an excellent denoising of the signal. So the take-home message is, even a very weak generative model can tell you something very useful when you do inference through it. So your model does not have to be a realistic generator of your data for inference to provide you with interesting things about it. This is a common misconception, I think, that people often criticize doing inference in a model by saying, why would you want to do inference in a model when it's so clearly a ridiculous generative model of your data? Okay? And that's also like saying, why would you ever want to use a linear classifier when your data distributions are so clearly non-Gaussian? Okay? So you can think about whether you really need to model the full data to do some auxiliary computation. Okay. Here are some results on single microphone separation. So this is a recording that has two speakers blended together. And then you can apply this denoising algorithm the same way, except instead of training one codebook on noise and one codebook on speech, you train it on one speaker and on another speaker, and you do exactly the same thing, and you can recover the sources. So this is the, I guess, I can get this right here. This is the true source, and this is the recovered source. And they're just mixed at 0 dB, so equal power. OK, so it's always good, another piece of advice for grad students in speech, of whom there seem to be very few, but it's always good to play demos. So I'm going to try here and play this little demo. So I guess what you'll hear is the original mixture, and then you'll hear the recovered sources and then the true sources. Maybe you won't hear anything. OK. I'm not sure what's happening. Let me just spend 5 seconds trying to debug this.
Using greasy wash water all year.
OK, let's start that again.
Ralph prepared red darker with greasy wash water all year.
That's the mixture.
Ralph prepared red darker with greasy wash water all year. She had your dark suit in greasy wash water all year. Ralph prepared red snapper with fresh lemon sauce for dinner. She had your dark suit in greasy wash water all year. Ralph prepared red snapper with fresh lemon sauce for dinner.
Okay, so it's a pretty good recovery. By the way, when I was a graduate student, I got the insane idea that I would record all 454 short Timid prompts myself on the same day so that we would have a stable recording of it. But wouldn't recommend that to anyone because you just start to go insane after a while. But anyway, that's the result of the denoising. And again, denoising, single microphone separation, they're both relatively sophisticated speech processing operations that we solved by doing inference in this super simple model. And the trick was that in the spectral domain, the max operation is really an excellent approximation of what's happening. That's the key piece of knowledge that you had to inject into the model to make some progress. So I'm now going to try and sort of bamboozle you a little bit. I just convinced you that it was great to work in the spectral domain because there's this max approximation. And now I'm going to try and convince you that for a different set of problems, you don't want to work in the spectral domain. You actually want to do something else. So it's always good to be a little bit mysterious, I think. This is highlighted in this quote by Roger Lincoln. Having told you now about working in the spectral domain, I'm now going to tell you about working in the time domain. So processing the speech wave directly in the time domain is it's kind of looked upon with a lot of suspicion, has a kind of dishonorable history in speech for, I think, sort of three reasons. One, variability is extremely high. If you say something and you say the exact same thing again, you look at the speech waves, they look very different. Okay? And then noise is a real killer. If you look at the speech wave when it's noisy, it's really hard to see what's going on. And of course, the noise does not obviously separate in any way from the speech wave. And what's really unfortunate, I think, is that there are some really super talented type A people who train themselves to read spectrograms. And then people thought, oh, well, if they can read spectrograms, that's it then. We don't really need any. We can just work off the spectrogram because, Victor Zhu can do it, right? So surely we can train a computer to do it. But I think that the frequency domain, while it's appealing for certain applications, there's a lot of cool algorithms that operate in the time domain. And I would really encourage anyone who's interested in speech to just look at the signal. So when I was here for the workshop, David Tolkien was also here. And David sort of took me aside one day and said, you need to spend like an hour every morning with waves just looking at the signal and the transcripts, because you're going to find out a lot of stuff that's really going to scare you. And sure enough, when you look at the signal, it's amazing. Clean speech has a lot of amazing structure in it. So we're going to try and look at that and just sort of leverage what's going on. So roughly speaking, in clean speech, there's three kinds of things. There's voiced segments. There's non-voiced segments, which are like fricatives and sibilants and plosives and all these kind of various unvoiced segments. And then there's silence. And voiced segments, of course, are extremely periodic. So when you look at a typical voiced segment of speech, it looks something like this. This is right where the voicing is starting. And you can see that there are these sort of warbles which repeat. And they're slightly different each time. And each one is related to a glottal pulse. And that's right there in the signal. It's really quite obvious when you look at the signal if you just stretch it out to any reasonable. Now, most people who work on speech recognition have never seen this picture, right? Because they just, the feature extractor extracts the features, and then you get the vectors, and it's, not really your problem. Now, that's, of course, an exaggeration, but it's really good to look at these signals. And in particular, you can imagine now, if you now start to think in my crazy mode of thinking, you can imagine a very simple generative model of voice segments of speech, right? So we're going to try and make a very simple generative model here, which is you proceed one pitch period at a time. And you make the next pitch period by copying the current pitch period. And you do a bit of transformation on it. You're allowed to do some stretching in the time domain. You're allowed to do some stretching in the amplitude domain. You're allowed to shift it a little bit. And then you add noise. So that's how we go from this segment to the next segment. Okay? So we take this segment, and we copy it. We do some transformations. We add a bit of noise. We copy that, do some transformations, add a bit of noise. That's our generative model for voiced speech. And now, the question is, if we put some reasonable limits on the transformations, and I show you a signal what choice of segment boundaries best models a given waveform? Okay? So if I just show you now the waveform, I tell you this is the speech waveform. Okay, where were the segment boundaries? Okay. And this is exactly inference in a generative model. You can formalize this, which we'll do in a second, and turn it into a problem of inference in a generative model. And as you'll see, there's an inference trick which allows us to do it. So by the way, in the last model, in the max VQ model, that model was proposed, that exact model was proposed by Varga and Moore for speech recognition. They didn't use it for signal processing. They used it for speech recognition. But it never took off because they missed the trick which allows you to do efficient inference. There's a magic trick in that max VQ model which allows you to do efficient inference. And Varga and Moore didn't know about that trick, and so they were never able to do inference in big models. I think if they had been, it would have worked much better. So again, here there's a magic trick which allows you to infer these segment boundaries. So first, let's just try and write down what the model is that I'm proposing here. It's a simple first-order Markov model on waveform segments, just conditioned on the previous segment. So if we use S to represent these segments and B to represent the segment boundaries and T for these transformations, what I'm saying is that the joint probability of all the segments factors into a conditional probability of one segment dependent just on the previous one and the relevant transformation. And then after that transformation, we inject some additive Gaussian noise. So actually, this probability, this factor here, is just the difference between the segment K and the transformed version of the previous segment under this Gaussian noise model. Yep. OK. So let's go back just to this model. Is this clear how I'm going to try and model successive segments? No. You're trying to find the boundaries. Yeah.
Okay. So go to the next slide again. You have B1 to Bk plus 1.
Yeah, and
Fixing B1 and Bk plus 1 to be the endpoints of.
right, exactly. So B1 is fixed to be the beginning of the signal. As you'll see in a second, it's not exactly the beginning of the signal, and Bk plus 1 is the end of the signal. And I just want to find where are the boundaries in between. But crucially, I also don't know the number of segments when you give me this speech wave.
So then what's S?
S is the vector of the subsection of the signal in the kth segment.
So then what's the probability of S of K given S of T minus 1? Because probability 1 vector given K.
Yes, you apply the transformation, the stretching and scaling, to the previous one, and then you add Gaussian noise. So our goal here is to do map decoding, Viterbi in other words, to find the most likely segment boundaries given this waveform and the model. That's what we're going to try and do. So we want to infer the best boundaries, and once you infer the boundaries, it's easy to infer the transformation. The best transformation, you just ask, how should I transform this to give me this?
Now, in the model that you wrote down in 1 and 2,
Yes.
you don't get any prior distribution over the boundary.
That's correct.
One in the bottom formula, that you just
Yes.
formatted.
Yes. So there's some restrictions on the transformations and on right. So here's an important regularizer which was actually proposed by John Hopfield several years ago. We were talking about this model, and this is another thing that you could take away from this, is that it's possible to talk about a model in 1998 and not actually get around to writing the code until 2003. But anyway, we were talking about this model, and he suggested regularizing it by making the boundaries only lie on zero crossings. And that's extremely helpful because if you were allowing the boundaries to be anywhere you wanted, you can imagine really pathological behavior where you sort of take one sample and you try and copy it forward, and then the transformation can do it exactly and things like that. It also makes the optimization much more tractable because instead of searching every possible position in the waveform as a candidate boundary, you only search the zero crossings. So we're going to restrict the segment boundaries to be at the 0 crossings, and you'll see that that gives us another advantage in a second when we sort of try and do tricks with this. So you can use a dynamic programming algorithm, it turns out, to find the segment boundaries. It's not the dynamic programming algorithm you think it is. It's not the dynamic programming grid where time goes this way and, boundary segments go this way and positions go this way. Because although the model is Markovian in segments, it's not Markovian in segment boundaries. In other words, if I fix this segment, segment k, and normally in dynamic programming what you'd like to say is if segment k is fixed, then everything that's happened up till now doesn't matter. What's the best place to choose segment k plus 1 and everything after it? But you can't do that because where you place segment k plus 1 depends on the previous segment, because the previous boundary, because you're going to copy this one forward. So you actually have to use pairs of boundary. Anyway, if you do pairs, then you can do dynamic programming. You have to discretize the scale transformation, and in order to save memory, you can use two tricks. One is to only do inference in between silence regions. So you just find a silent period, there's some speech, and then there's another silent period, and you just say, imagine that that's its own utterance all by itself. Forget about, just infer on that separately. That keeps the complexity small. You can also use this sort of iterative solver to keep the memory footprint of the dynamic programming small. Again, these are all sort of random street fighting tricks that you don't need to worry so much about. But just one sec, Bill. Let me just show you. But the result is this is the speech wave that you're given, and this is the inference that you get at the bottom. This is the map. And I've just put up arrows in the locations where it's inferred a segment boundary. And we're doing something really insane here. We're applying the voiced speech model to the whole speech wave. We're just saying, voiced, unvoiced. Let's just pretend everything's voiced. So in the unvoiced regions, the model just goes to town. It just takes, this noise, and it tries to copy it. It does the best it can. But in the voiced regions, you can see it's really hitting the segment boundaries properly. And there was, this is just dynamic programming in the model I told you about before. So Bill, I guess, and then Jason.
So the way you describe the model, if I understand, is you sort of grab a segment.
Yep. So we take this guy, we copy him forward, we do some stretching, scaling, and then the same thing. Oh. Then you take that one and you copy it, that one you copy it.
So it's not like you're taking the word at the beginning.
No. It's a first order Markov model in segments, yeah.
But at each point when you do that, there's a choice of several different districts on the top of this previous segment. Right?
Oh, yes. Yeah.
So you sort of do it the time backwards you can go for that state.
No, it turns out that you can do the full dynamic programming. The way that plays out is that you say, if I could find an eraser, I wouldn't have to go over there yet. You ask, what's the cost? Let's say that this is A, this is B, and you're looking for some segment C here. The dynamic programming table you build holds the cost of the best segmentation with A and B. Okay? So you say, what's the best cost I could achieve in the future if B is a segment boundary and A is a segment boundary? Okay? And now the way you update this in dynamic programming is you say that the cost of CB is the min over all choices C of the cost of AB plus the transformation cost going from C to B. That's the way you update. So you say, pretend I had these two as segment boundaries. What is the best segment boundary I should pick for C? And the way you get that is by proposing a segment boundary, figuring out what the cost would be under this transformation model, and then adding that to the minimum cost you already know.
How do you ensure that you don't choose the neighborhood of zero crossings like the zero crossing?
Yeah, so we enforce there's a minimum and a maximum distance between zero crossings. And actually, right now, the minimum distance is 0. So we are only enforcing really a maximum. But it's easy in the dynamic programming to enforce a minimum also if you needed to. But the model never chooses to put them close together because it gets more mileage out of copying these bigger segments.
What other than the maximum prevents the model from saying you just have one long segment and you never copy it?
Yeah.
There are two possible answers. One is that it's prior, and the other is that it just gets more mileage from.
No, it's just because we have this maximum.
That's
maximum.
okay.
Yeah.
Are you going to talk about the structure of transformation? Is it parametric or is it linear?
I can say a little bit more about it. The transformations are just the ones I described here. Time dilation and compression, amplitude scaling, and amplitude offset. And if you give me the segment boundaries and you're willing to discretize time dilation, then you can solve for everything using linear regression, right? Discrete linear filter. So.
Yeah, sorry, so just for clarification, I guess that's the question I was trying to ask about the max. So is the reason that you want that because there's this bias against having short things because you're just multiplying the probabilities together?
I don't think that's exactly where the bias comes from. The reason is just really that we think of these as pitch periods, and we know that there's some, minimum pitch beyond which it's unreasonable to infer. So that's how we do it.
So even with the max, why don't you copy two pitch periods at once? In other words, why don't you think that the pitch period is actually twice what it really is?
You can do that, but imagine you're copying double pitch periods. Pretty soon you're going to end up in a position where you get a terrible match, because when the voice segment ends, you'll get a sort of halfway voiced period, and then you'll get a really terrible match when you do that copying.
If there's an odd number of pitch periods. If there's an even number, you might be okay.
Well, if there's an even number, then when you go to transform it, you'll have to do quite a lot of, but yeah, it's possible. Sometimes you see errors where it does that, but it's generally pretty good. Okay, so this is the picture here. This is the segment. So you can think of this as I give you a speech signal, and you give me back some markings in the speech signal, which just tell me what are the atomic units. What are these little subunits of the speech wave that you shouldn't be messing with, that you should keep together, because they're pitch periods, they're glottal pulse pitch periods. And now once you have those markings into atomic units, you can do all kinds of sophisticated things just, in the simplest way. So here's time scale modification for dummies, right? What are we going to do? We want to make the speech wave sound faster, so we're just going to drop out segments. Because these are pitch periods now, and they all start on zero crossings, so enforcing waveform continuity is trivial, right? And we're not going to change the pitch, and we're not going to change the formant structure. That's perfect. That's what we want. So we just drop out. So this is the original input source. This is a little window into it. If I want to go faster, I just drop out every other segment. That'll go twice as fast. If I want to go slower, I just copy every segment twice. Right? So this is the simplest timescale modification algorithm in the world. Right? No phase reconstruction, frequency transformation.
So you sort of redefine pitch period.
Uh,
Like the smallest interval that you can get sort of a repeatable little chunk.
Yes, exactly. And you can tell that I don't really mean pitch like glottal pitch because I'm doing it in the unvoiced regions also. So, yeah.
Few years back, I worked on this problem, and I remember inventing a very standard algorithm, which is to set the energy and has some sort of autocorrelation filter, which checks for the pitch period and it gives workable solutions. And I'd be interested in knowing how your method compares to that. And it's a very standard algorithm because I found it on some paper on the web and implemented it.
Right.
I was doing this for a speech synthesizer, and it worked very fine for me.
Right. So I'm not sure if I can give you a comparison, but I can play you another demo. How about that?
Yeah. Before you play the demo, let me just comment on something that Jason said.
Okay.
Even if you had an even number of pitch periods,
Yeah.
at least the way you described it, it looks like taking something which is two pitch periods
Yeah.
would involve then requiring a single dilation shift
Yes.
and
Yeah,
scaling
exactly.
for the next one, which is necessarily worse
It's not necessarily worse. It depends what happens, but
Maybe
yeah.
it goes on that, and also if you have some cost to generating lower pitch period, because there's, you know, if you think about the probability of generating the very first one before you start copying it,
Right.
and you've got some model on that or MTL, or
Right, right.
you've got a prior on one of those things, you can fix this.
In fact, my question was going to be more about how to control the smallest pitch period.
Yeah, and anyway, it turns out that if you restrict to zero crossings, you don't need a further restriction about smaller things. But if you didn't have that restriction, then you would be really in trouble.
Zero crossings and your DC shifts kind of contradict each other. If you're looking at zero crossings, how come you allow DC shifts?
Well,
That changes the location.
you know, of course, that we're working in discrete time, right? And the signal never goes to zero. When I say zero crossing, I mean the sample before it went through zero or the sample after it went through zero. And so you can get a better match by doing translation, right? Of course, no discrete time signal ever hits zero. So, OK, let me just play you this demo here.
First commodity, appeal the expulsion and fine to the CFTC.
OK, this is the stupid way.
First commodity, appeal the expulsion and fine to the CFTC. First commodity, appeal the expulsion and fine to the CFTC.
OK, and then there's another demo on here.
First commodity, appeal the expulsion and fine to the CFTC.
So all I did there was I took each segment and I just extrapolated it using its Fourier coefficients, and I got rid of the following segment. So that halves the pitch period and keeps the Foreman structure. So maybe I'll just play these timescale demos again very quickly.
First commodity, appeal the
That's the
expulsion
original.
and fine
And then
to
there's
the
subsampling in the
CFTC.
time domain. And this is fast.
First commodity, appeal the expulsion and fine to the CFTC. First commodity, appeal the expulsion and fine to the CFTC.
OK, so that's just copying every pitch period. So, oops. So there's many other things you can do. You can do voiced or unvoiced detection. Now that you have these segments, you can just take each segment and reconstruct it using a small series, cosine or sine series, and then just look at the error. And in voiced segments, sure enough, the error is pretty low. And in unvoiced segments, the error is terrible. And then you just put a threshold on that error. You can do voicing detection. And then you can do pitch tracking for dummies, right? 1 over the segment length. That's your estimate of the pitch, right? And just to convince you that I'm not completely going nuts here, we just did these tests on the Kiel database. So Kiel is a database where they actually had a laryngograph. That's like another physical hardware device that measures pitch. So, so they give you a reference, pitch reference, and you can compute pitch. And so here, the blue circles are our estimate of the pitch, and we only put a blue circle when we think the segment is voiced. And the red crosses are the Kiel reference from the laryngograph, and they only plot a red cross when they think it's voiced. And you can see that the estimates are really, they line up quite well. Now again, there are lots of other pitch tracking algorithms, but none of them quite as stupid as take 1 over the length of the segment. Right? And so you can show the results of this voicing and pitch detection right on the spectrogram. Here's the original spectrogram, and then wherever we think it's voiced, we're going to overwrite the spectrogram in blue with the harmonic stack. So you can look and you can say, oh, here's some down sweeping pitch, and we've put that on there. That's just a way to display what you're discovering about the signal. OK, so in the last few minutes that are left here, I want to just give you one more generative model that you can do inference in for a completely different speech processing task. So you'd think, well, time domain processing, frequency domain processing, so where is he going now? And I think a point that, that's been emphasized to me a lot, which I think is very helpful, is always ask yourself, in what domain does it make most sense to do some computation? What representation is the most sensible representation for doing the computation? So I want to study a question about articulatory inversion, so speech movements, the movements of the mouth. But I want to cast this as a game. It's always after 5 o'clock. It's always good to motivate people with a little cookie. So here's a game. So the game goes like this. There's some map here, which has some numbers on it. And I'm going to stick my pen down and wander around in this map. And then I'm going to read off to you in order the numbers that I saw. So you get to see this. You don't get to see this. And your job is looking only at this to reconstruct the map. Okay? That's the game. Now, if you think about it for a minute, you can realize that, well, you'll never be able to reconstruct the rotation of the map or flips of the map. So, but when we say reconstruct, let's just mean the topology, up to rotation and flipping, right? So there are many sort of computer science-y algorithms for this, right? Like adjacency. You see 5 and then 6, and so you know 5 and 6 have to be neighbors. The rules of the game are I'm not allowed to lift up my pen. So everything that you see adjacent to each other is neighbor. And you can sort of work things out using these adjacency graphs, okay? But the computer scientists can run, but they can't hide. I can make these jokes now that I'm employed in the computer science department. So now we're going to make the game harder, right? We're going to make the output process noisy. So every once in a while, I'm just going to lie to you about the number. I'm just going to put an incorrect number there. But of course, I'm not going to circle them in red, right? And then furthermore, I'm going to repeat numbers. So here's a number 1 in the map, and here's another number 1 over here in the map. And here's a number 10, and here's another number 10. And when you see them, that's your fault. You know, they're just merged together. Tough luck. And now, the question is, can you still recover this map? And the answer is yes, if the sequence is exciting enough. If I'm really boring and I just sort of do this, and I just show you 1, 11, 1, 11, obviously you can't recover the map. But if I really move around the whole map, you can, but these deterministic methods based on adjacency graphs are not going to work. So this sort of sounds like a job for statistical learning. And the question is, what model should we use? And the model is a very simple model. It's called a constrained hidden Markov model. And the idea is really, really simple. The idea is you can model a spatial dynamics like the one I was showing you in a hidden Markov model by just discretizing the world and thinking of each cell in that discretized world as a state in the HMM. And now you pre-program the transition matrix of the HMM to only allow transition between spatially adjacent states. So every valid state sequence in the HMM under this constraint corresponds to a connected path in the state space. So you might say, oh, each little cell in this cube here is a state in the HMM, and I'm only going to allow this state to transition to its neighbors. All the other transition probabilities are going to be 0. So now I've created a weird kind of HMM in which every state actually has a physical location and only transitions between physically adjacent cells are permitted. Okay? So to set this up, you have to choose the dimensionality, whether it's 2-dimensional or 3-dimensional or whatever, and some kind of packing, cubic packing or hex packing or neighbors, whether you're face neighbor. Anyway, you have to make some of these choices, but once you do that, you have this sort of HMM. And now you can see that this game is exactly HMM learning, right? The game is I show you an observation sequence, you estimate the output parameters in each cell, and because there's noise, you're going to estimate, a lot of probability on the correct number, but a little bit of probability on all the other ones. That's the noise, right? So this problem is exactly the problem of HMM learning there. So the application I just want to quickly show you here is a very old problem, which is, can you hear the shape of the mouth? That's a joke about a Mark Katz paper, Can You Hear the Shape of a Drum? So that's a really awesome physics paper, for those of you who haven't read it, which answers the question, are isoperimetric membranes isospectral? And which informally is, if I bang on a drum and you listen to the harmonics, can you tell me the shape of the drum head? So I won't tell you the answer to encourage you to read Mark Katz's paper. But anyway, here the question is, can you hear the shape of the mouth? So what I want to do is I want to build a machine that goes from the waveform to estimating something about the way that the mouth moved. And you can think of this exactly in terms of the game I showed you before. The configuration of the articulators is where you are in that map. And the sound that comes out is what number I show you. And because your articulators are these physical things, they have to move in a slow and smooth way. And so I show you a sequence of numbers, and you want to figure out where you were in the map. That's roughly the setup. There are some problems with this. Oops. But I just want to tell you that there's a great data set from the University of Wisconsin-Madison. It was collected by John Westbury and his guys. And I'll just show you this picture here of the results, which you just do exactly what I said. You train this hidden Markov model in an unsupervised way on the sequences, and you do inference in the hidden Markov model. Now, of course, when you infer, what you infer is some abstract state space. So you need a little bit of supervised data to line up that abstract state space with the actual measurements. Once you do that lining up, you can do this kind of recovery here. So the dotted lines show you the estimates of the articulators, and the solid lines show you the true values. So it's certainly not perfect, but it's doing a pretty good job of estimating the articulators. This shows all of the articulators. This one is just the 2 beads on the tongue. And these 2 lines are vertically separated by the measurement error of the machine. So you can answer the question, is this a good result or a bad result? It's on the order of the measurement error of the machine is the recovery that you can get. OK, so I'll just finish up here. I've tried to convince you using these 3 simple examples, this max VQ model, this segmental waveform model, and this constrained HMM model, that probabilistic inference in very simple generative models can be used to use a lot of different speech tasks. And taking advantage of key structure that you know about the problem is really essential. If you build that structure, those constraints, into your generative model, then you can get surprisingly complex speech processing from a very simple generative model. And even when the generative model is not realistic, the results of inference may be very informative about the original data that you put into it. So the sort of moral, the take-home of the story is that the next time you have a signal processing task, you should entertain the intellectual program of dream up a crazy generative model of your data in which the thing you want to calculate appears as a hidden variable, and do inference, rather than the intellectual program of scratch your head really hard and read lots of old papers about techniques you don't think are very good, but you don't know what else to do, and then try and get it to work by hook or by crook. So I hope that these examples are somewhat compelling, and that's all.
Last example early on, you had something in green that was like if the signal is sufficiently exciting.
Right. So if you remember the map, of course, if I didn't really move around very much in that map, you wouldn't have any chance of figuring it out. Like if I just stayed in one place here. So, but that concept has been formalized in control theory under the term persistent excitation. So it's really exactly analogous to the issue of identifiability in a dynamical system. Gert?
So in your first 2 approaches, have you tried to combine the 2 to do some separation of
Right. No, we haven't, but we're working on that. So what Gert is asking is the $64 question, right? You have this sort of waveform model, and you were working on separation. Can you dream up a generative model in which 2 people are talking and operate somehow in the time domain and do inference? No, I haven't, but I'm trying. So yes, a very good question. It's a good direction, I think. Back?
How well does the second model work when you have noise?
Ah, yes, the inevitable. So Zach's question is, how well does the segmental waveform model work when you have noise? Roughly speaking, the answer is it works terribly. It's not quite that bad, but it's very hard to see the periodic structure in the voice sections when you have a lot of noise. Yeah, the zero crossing. The zero crossing regularizer is a bit of a different issue, but you can try and run this model simultaneously in certain subbands. Okay, so you can do a multi-band decomposition. You can run it in each subband, and then try and figure out in the bands where the model seems to be doing well, we're going to think of those as the signal bands, and in the other bands, we're going to think of those as the noise bands. But then everyone has to synchronize their inference, and that it gets a little bit more dicey. So the 0th order answer is it doesn't work, and the 1st order answer is you can maybe make it work in multiband.
No, I would actually worry about that approach, because if the signal was really periodic and then it had noise, then in the band of interest, it's steady, and finding pitch periods in a steady signal is going to be really hard.
I didn't mean to imply that you would measure the power in the band. I actually mean a multi-band decomposition. So imagine you do a filter bank. Then it's not going to be constant. It's going to be periodic at the center frequency of that filter bank.
The question I had was actually related to this, that you have a shift, minor scaling,
Yes.
and what else? 2 or 3 operators which could move.
Yeah,
the
time
signal.
dilation, amplitude scaling,
And then
amplitude
whatever
shift,
is
and
left,
noise.
The residual you model it
Yes.
as a Gaussian.
Yes.
I guess it sort of affects the question about noise, because my question to you would be, what is the nature of that noise? Is it really Gaussian? Because also you're assuming...
Oh, absolutely not. But the signal isn't really Markovian in segments
No,
either,
that.
right?
What I'm thinking is that compared to additive noise, which might be truly Gaussian, this reconstruction error may not be Gaussian. That might be a way.
I see. Yeah.
Because if you allow a
It's
certain
like-
range of amplitude scalings and a certain time dilation, I could imagine that more often than not, you're off by a little band everywhere. And
Yeah.
if you looked at the, I don't know, the...
It could be. I think this is like arguing about the paint job on a horse-driven cart. I mean, the model is so crude that really whether we use Gaussian noise or some maybe heavier tailed noise, or whether we try and take into account the correlation, it's, I think that issue is much more dominated by the fact that we're applying this voiced model in the unvoiced regions. That's a really terrible thing to be doing. So the next step, of course, is to have a switch where you say, oh, I'm in the voice mode or I'm in the unvoiced mode.
How would you validate such outcome? Because essentially you build models that you cannot generate from. I mean, you cannot trust that it's going to work because the generation is good. So you cannot. So, and now you show us one example where it works. But
Right.
how can you tell me that on the next example it's still going to work?
Yeah, I mean, the way to validate it, which I freely admit I haven't done, but the way to validate it would be to make this plot for lots of data sets and lots of algorithms and show that your algorithm is competitive. But that's not the game I'm trying to play. I'm not trying to invent the world's best pitch tracking algorithm. I'm trying to convince you that the same model, which is a terrible generative model of speech, can simultaneously do pretty good pitch tracking, pretty good timescale modification, not so bad voice-to-unvoice detection, gender conversion. Like, I'm trying to convince you that you've really learned something about the signal, right? If you take a pitch tracking algorithm, it might be a very good pitch tracking algorithm, but how do you do timescale modification with it?
Yeah,
So.
but you still need to convince us.
No, but I was never trying to convince you that I have a competitive pitch tracking algorithm.
But you might be trying to convince us that if you wanted a competitive pitch tracking algorithm, you just improve your model and still do it.
But what about some speech processing problem for which there's no algorithm? Like, I mean, if you had a really new speech processing task, you might consider designing at least the first version of your algorithm as an inference algorithm. Maybe. Bill?
What you just said, I mean, so what did you learn? I mean, you have an unsupervised way to segment the waveform in this case.
Right.
So usually, when you have a generative model and you say that something is learned, you estimate some parameters and you can apply the model to some other data and you say it did a good job or not.
Right.
But here you're not really in that situation.
No, and that's because we didn't really train this model on any data. And that's simply has to do with the fact that it has so few parameters that we just set them by hand and it sort of was okay. The maximum segment length, for example.
So what you learned is that this really simple approach works.
Yeah, I mean, what you mean what you learn about the signal? What you learn about the signal is you get a segmentation of it into atomic blocks that are really, they come at the pitch rate in voice sections, and they contain the correct formants. But you're right, there's no quantitative measure that's analogous to generalization performance.
No, and you have as much data as you started out with. I mean, you have,
Yeah.
I mean, a lot of times the learning is like a compression of some sort.
Yeah, no. It's this is just a way of doing inference in this.
Well, but there is effectively a compression there, and that you could represent every signal, since it's a transform. I'm sorry, every pitch variant using fewer bits because it's a transform of the previous variant. I mean, you have to represent the transform plus the move.
In the VQ approach, where you take max, so this will work if two sources are the same level.
Yeah.
Once low amplitudes involved.
Right. And so, so Gert is pointing out that this max approximation is really only good around 0 dB in very clean speech. If you have noise and the signals are at slightly different levels, then you're going to have a problem. I don't really know exactly how to fix that, except to try and, one thing I have tried is to put in just a global level for each source and to try and infer that in the model. But the problem is that then you can do a good job at reconstructing the loud source, but you can't do a good job at reconstructing the quiet source because you don't have enough energy left. When you mask off the spectrum, what you're left with are so few pixels that you can't, it's not, the code isn't so redundant that you can fill it in still. I don't know how to overcome that. I would say that if you have a noisy, quiet source in the presence of much louder distractors, it's going to be quite tough to pull it out unless you have a stronger model.
Well, if you know the load source, why can't you just mask the load source and you get the other one?
Well, because there isn't enough energy of the, like if I put a microphone in this room, it's now recording a mixture of, everything that you hear in this room plus some coupling from someone talking in the other room, in the other building, right? But that's not, we can't just remove what we hear. Like, there's just not enough energy at some point left in this simple model. If you just mask off all the pixels that belong to the loud source, what's left doesn't have enough energy for it to be intelligible to you. So you could do some more sophisticated separation at that point, but not this masking, I don't think would work.
Okay, well, let's thank our speaker again for Thanks very much.
Oh, thanks, Jason.
What were your observations in
Class until 12 and
What were the observations were